simplified radical expressions. Yay.
You need this. Algebra 2, you need it.
Yep. Especially the rationalizing the denominator. I don't think you guys have done that for a while, or if you've ever done it at all.
And this is always on standardized test too.
Okay, so while I'm teaching, you guys need to not talk because we are filming for Macy, and when there's a lot of background noise, I think it will be hard for her. Okay, just don't talk. Don't socialize while I'm teaching a lesson. Okay, you'll have plenty of time to do that afterwards. Pay really close attention. You can get through this, and then you probably get your homework done. All right, so that right there is read the square root of 25. It means one of the two positive equal factors of 25. And here's some examples of perfect squares. The square root of 25 is the square root of 5 times 5, which is 5. The square root of 36 is 6, so on and so forth. And then you also do variables, and you'll get really into that in algebra 2 with variables, okay? But for geometry, we're mostly going to be doing the numbers because we're doing right triangle stuff with the special right triangles. But if you look at this, you have a to the 6th. That can be written as a to the 3rd times a to the 3rd. And so the square root of that is a to the 3rd. So there's just a couple examples of variables too, just so you can see how the pattern works. Square root of a is called a radical. A is called the radicand. Always have this next part close at hand when you forget how to work with radicals. If you have the square root of x times the square root of y, you can write that as the square root of x times y. And you can also go backwards. And that's what I did here. I just missed a step though. So right here, I can write the square root of 18 as the square root of 9 times 2. And so I can write that like this. I can put the factors under here, and then I can rewrite it as square root of 9 times square root of 2. That's why I can do that, because it's one of the general rules for radicals. And that's this one right here. Okay? We also have quotients. The square root of x over the square root of y is equal to the square root of x over y. And to undo a square root, or sorry, to undo a square, you square root it, and to undo a square root, you square it. So like how you have to multiply to undo division, you have to add to undo subtraction, you have to square root to undo square, and you have to square to undo square root. Okay? So here's some actual numbers that show you how to do it. So if I have square root of 2 times square root of 5, that is the square root of 10. If I have square root of 18, that's equal to the square root of 9 times the square root of 2, and that's the one I have there. Then you can simplify it to 3 root 2. If I have the square root of 8 over the square root of 2, that's equal to the square root of 8 over 2. What's 8 divided by 2? 4. What's the square root of 4? 2. So the answer to this right here is actually 2. Okay? And then right here I have the square root of 159 squared, and right here I have the square root of 159. You're squaring the square root, and that's equal to 159. Okay, and then we'll get into these. I don't know if we have to do these in geometry. We might. But when you add square roots, is what you do is you treat them just like a variable. So if I had 2 apples plus 3 apples, that's equal to 2 and 3, 7 apples, right? So this right here, the rule is you just add the exponents out in front as long as what's underneath the radical is the same. So right here, since I have 2 square roots of 3 plus 4 square roots of 3, that's just 6 square roots of 3. That's just like adding 2x plus 4x. Okay, you can treat that radical as long as they're the same, just like you would a variable. Alright, so simplifying square roots. Sometimes it is convenient to leave square roots in radical form instead of using a calculator to find approximations, decimal values, and you'll be asked to leave it in simplest radical form. Okay, look for perfect squares. That's why I asked if you knew the first 10 perfect squares, because you really need to know those. And it'd be really good to know the first 20. Okay, if you know the first 20, you're even that more ahead of the game. Okay, as factors of the number that is inside the radical sign, radicand, and take the square root of any perfect square factor. Multiply the root of the perfect square times the reduced radical. And that's what we did right here. I found a perfect square, which which was 9, and so I took the square root of 9, and then I multiplied that number by the reduced radical, and that's what they're talking about right there. Okay, so here we have some examples, and it's like what we did in our bell work. Is what you want to do is look at the number, and you want to ask yourself, is there a perfect square in that number? And if you don't know, can you just start dividing some of our perfect squares into the number until you find the one you need? Absolutely, okay? So that ends up being square root of 4 times square root of 5, which is 2 root 5. 48 is equal to 16 times 3, so that's root 16 times root 3, which is 4 root 3. So that's when you look for perfect squares in the number. You can also do a factor tree, okay? I never do it this way. I always look for perfect squares.
I always factor.
I always look for perfect squares, because to me, it's just faster. Okay, so factor tree.
I think it's easy to divide by 2, but hard to divide by 16. That's why I go with even.
If I divide 96 by 2, what is that? Because 96 is an even number. What do I get? Okay, I'm going to keep dividing by 2 until I've exhausted it. What's 2 divided by, or 48 divided by 2?
24.
And what's 24 divided by 2?
12.
And what is 12 divided by 2?
6.
And what is 6 divided by 2?
3.
Okay, you guys should be writing this example now. This is the factor tree. Okay, so in this box right here tells you what you need to do. Factor what's inside the radical completely, and that's what we've done. We've got it down to all of its prime factors. Okay, we went all the way down. Okay, for any factors, number 2 says, for any factors that appear 2 or more times, bring out pairs of factors. When bringing out pairs of factors, each pair becomes a single factor outside of the radical. Okay, so let's do what they just said. Let's find pairs. So here's a pair. Okay, so I can bring that outside of the radical. Here's a pair. So I can bring a 2 outside the radical. Do you see when I bring it outside, I multiply? So here's 2, so I bring 1 out. Here's 2, I bring 1 out. Then whatever's left underneath, you multiply it back together. And that's right here. Only single factors should be left inside the radical, and then I put multiply them. So my answer to this is 4 square roots of 6. Okay, there's a factor tree. Otherwise, take 96 and divide it by perfect squares. And is 25 going to go into 96?
No.
No, so you're not even going to try that one. 2's kind of small. So I want you to just do some perfect squares into 96 till you find the biggest perfect square. Because that's what we did above on those other examples, if you don't like factor trees. So square root of 96 is equal to the square root of 16 times what? 6. Right? So then you can write that as the square root of 16 times the square root of 6, which is equal to 4 square roots of 6. When I was looking for different things to put on your study guide online, I found probably 5 PowerPoints teaching you how to do radicals. Teaching you both ways. Teaching you with this way and teaching you this way. All I put in, I just Googled simplify radicals, leave them in radical form. I don't know, I wrote that in there, whatever. There's so much. I was like crazy. There's some really good slideshows. So if you ever have trouble with things, you guys should really use the internet more. When I teach something and you don't understand it, then you should get online and have someone else teach it. Because there's somebody out there that's going to explain it better than I do. And I seriously found 5. And that's just with looking within the first couple of, you know how they have, you can keep going on the bottom. So I went 1 through 10, and then I went over to like 13 and 14, and then I started finding all these slideshows done by teachers, teaching you how to do these.
The biggest concept is you have to have 2 of something to bring it out, because you really have to grasp that, because pretty soon you're going to do cube roots or fifth roots, and if they don't understand that concept, that's when it gets hard. So the reason we look for perfect squares is because it's 2 of something to bring 1 thing out.
And later when you get to like cube roots, you have to look for 3 of something.
3 of something to bring
6
1
roots,
thing
you have
out.
to look for 6 of
That
something.
concept is really, really important. That's where they struggled in Algebra 2 this year. They didn't understand that concept.
Okay, so let's look at 240. I'm gonna do a few of these with you guys, and then you're gonna do the rest of them on your own. Let's do the first three together. So 240, we're gonna do it. I want you to find a perfect square that goes into 240. Start using your calculator. You found it? What is it? And what is it? 16 times what? 16 times 15? Okay, so then I can write that as the square root of 16 times the square root of 15, which is 4 square roots of 15. Okay, so now let's do it with the factor tree. I'll do it up here, you don't have to do it on your paper. Because some people just like factor trees better. Okay, if I divide that by 2, what do I get? 120. If I divide that by 2, I get? If I divide that by 2, I get? 2, I get? And then I get 3 and 5. Okay, so now let's do our pairs. So here's a pair, bring it out. Here's a pair, bring it out. What's left inside? Okay, so the answer is 4 root 15. Is that what we did when we looked for perfect squares? Yes. So you can do it either way. All right, let's do this one. I want you to find a perfect square of 525. Just try some until you find it. And then tell me what it is.
25.
So 25 times what gives you that? 21. Okay, so that's square root of 25 times square root of 21, which is 5 square roots of 21. Okay, so now I'm going to do a factor tree. Okay, if I do a factor tree, what is 525 divided by 5? I started with 5 because there's a 5 there. I'm not going to start by 2 because 2 doesn't go into 5. What is it, 105? Okay, and if I do that by 5, what do I get? Okay, and if I get that, that's 3 and 7. So here's a pair, because it's square root, bring it out, and what's inside?
So if you could know, like, you simplify
I'm
it
loving
by
it.
3 times 7, you would
Yes, you have to multiply back what's left underneath. You wouldn't go, I don't want it to look like this when you're done. I don't want that. I want you to multiply back together what's underneath. And you know what? Could you have stopped right there in order to give me my answer? There's a pair, bring it out, leave what's underneath. You could have stopped right there. But I'm just showing you that you just keep going until you have all these two things because you're taking square roots. Okay, we have a negative out here, so let's just leave that. What's a perfect square that goes into 600?
25. 100.
I would say 100.
Always use 100.
Always use 100. So now we have negative square root of 100 times square root of 6, which is negative 10 square root of 6. That negative is on the outside, so you just leave it on the outside, and you're done. Okay, I want you guys to do the next 6. Work with them at your table, and I'll come around and check them. And some of you might already be done, because you get it. And then we're going to rationalize some denominators. You're still a perfect square in 8. So keep going on that one. And the rest are right. You're still a perfect square in 8. So do number 6. Keep going. When you guys get number 6 done, tell me. And then I'll have you help check people's faces. Okay, good. If I'm helping someone else, you can help them so we can get through this quickly. Then we'll have more time to do homework at the end of class. So do it either way. Find perfect squares or do a factor tree. You guys figured out, we're having a good discussion. They didn't factor it completely. On 72, they did 9 instead of 36. See, you can still factor that though, because 8 has a perfect square.
That's why I always
So
start
you're
with
not done.
2, cause sometimes then you're automatically at a perfect square.
Yeah.
I stop when I get to perfect squares.
Yeah.
I mean, I don't have to.
Wait, you said just number 6?
Anything that's 10, I always start with 10. I don't necessarily always start with 2.
What's the square root of 36? Why do you have that underneath the square root?
What? Okay.
Erase that.
So-
Always write the perfect square first. That'll help you with, that'll help you with access.
So it didn't approximate you.
On what do you mean?
3 and 2 don't have partners, so they have to stay under. If it doesn't have a partner, it
Of
can't come out
course,
naked.
of course you can. You need to.
Okay.
Yes, you can use any perfect square you want. Did you guys understand what you did?
Yeah.
Yeah, you can't leave something underneath the radical that still has a perfect square in it, because it can still be brought out. And that's why sometimes factor trees are good, and like Ms. Shiloh said, sometimes just take that number and divide it by 2, and you'll find the perfect square on the very first
Or
try.
10, or 100.
Yep.
I mean, easy one, 5 sometimes.
But if
I
you would have
mean,
divided 72 by 2 right off the bat, you would have gotten 36, which is a perfect square.
And you'll recognize perfect squares sometimes once you see them, but you might not be able to look at the number and know which perfect square goes into them.
Hey Jared, go back there and check Austin's so we can get moving. Good. Will you check with, check with, yeah, check with her. Okay. Awesome. Now we're gonna talk about rationalizing denominators. I liked how when I found this is from an honors geometry class. I liked that they showed to build a 1, that you're not changing the value of that, you're just changing the way it looks, or getting the radical out of the denominator. So they tell you to build a 1, so you look at what's underneath, root 5 over root 5 is just 1. So you're just multiplying it by 1, so it doesn't change it. Okay, are you ready? So we're gonna rationalize the denominator now. You can't have an answer with a square root in the denominator, because a square root of a number in the denominator is an irrational number. So we want to rationalize the denominator. We want a rational number in the denominator, and this is how you do it. So if your fraction has a denominator with only one term that contains a radical, like this, build a fraction with the radical in both its numerator and denominator. This fraction will always have a value of 1. So if I look at that one, I know I can build a 1 by taking root 5 over root 5. Because if I take this right here and I multiply it by root 5 over root 5, am I changing the value of this? No, I'm just multiplying it by 1, I am, right? Aren't I? Yeah. That sounded weird. Okay, so then you just multiply across. You have 3 times square root of 5, which is 3 root 5. Now what's root 5 times root 5? That's root 25, right? So that's equal to what? 5. So you've rationalized the denominator. 5 is a rational number. Right here, Zach. Square root of 5 times square root of 5 is square root of 25, which is equal to 5. But watch this. Let's just look at a few things. What's square root of 2 times square root of 2? Square root of 4, which is 2. Square root of 3 times square root of 3 is square root of 9, which is
3.
square root of 4 times square root of 4 is equal to square root of 16, which is
4.
4. Do you see the pattern? So what happens basically every time you have a square root times itself? You get what?
It's that number.
It's just the number underneath, right? So if you remember that, then this is never going to be hard. It's that simple. So look right here. We have 9 over root 6, so we're going to build a 1. So since this is root 6, we're going to do root 6 over root 6. And we're going to multiply that by our original radical. Okay, 9 square root of 6, you put that there. Square root of 6 times square root of 6 is 6, because it's just the number underneath. Now we have 9 over 6 though. Can that be simplified?
It can.
Yes, so you gotta divide by 3. So this is 3 square roots of 6 over 2. You have to go all the way. You can't leave it 9 root 6 over 6, because that's not simplified all the way. So let's do a couple of these and then I'll have you. Alright, so I'm gonna build my 1. So that's gonna be root 10 over root 10, right? We're following the pattern. Okay, so then I get 4 square roots of 10 over, what's root 10 times root 10? 10. Am I done?
No.
No. 2 root 10 over 5. Now I'm done. Okay, let's look at one that's let's look at this one right here, okay? When I look at, there's several ways you can do this one. You can go ahead and do root 48 over root 48, but how many of you think there's a perfect square in 48?
I do.
Thanks, CJ, for being so exuberant. Find it. Find the perfect square in root 48. Let's go ahead and simplify that first, and then we'll do it the other way too. So that's 9 over root 16 times root 3. Is that what it is? Okay, so that's equal to 9 over 16 root, not 16. 9 over 4 root 3. You guys agree? Okay, so I'm going to take 9 over 4 root 3, and I have to rationalize the denominator. So I have to multiply top and bottom by root 3. So I get 9 square roots of 3 over 4 times what? 3. Okay, so that's equal to 9 square roots of 3 over 12. I still need to keep going, don't I? That's equal to 3 square roots of 3 over 4. And there's your answer. Okay?
I hope that's as hard as it is.
Well, there's another bigger one right there. Square root of 8 has a perfect square in it. Okay, I want you guys to do the rest of these. I want you to do all of them. Okay? So work out the other 8. I bet you could get those done in the next 8 minutes. 1 minute problem.
Yep.
Got what here?
Working 2 square root of 4. 2 square root of 2 of 4.
You need, what comes out of 8? What comes out? A 2 comes out. So what's already outside? 4. We have 4 times 2 on top. What do you have on the bottom? We have 8 on the bottom.
How'd you get 2?
We have 8 8 over 8 square root of 2, so 8 over 8 cancels, so you're left with
Oh.
square root of 2. You multiply what you brought out, just what's already there.
4 times 2 is 8, over h is 1,
Yeah,
which makes it 16, or, sorry, oh, so it's
so the 2 cancels here.
square root.
That you would have been in there.
I started going a different way.
Oh, but do you see that? That just simplifies it.
Oh, sorry.
I'll come around and look at the first ones. I worked those out so Macy could see them too, but I'm just gonna look at your first ones. Okay, so let's look at that one right there. So 4 square root is 8, okay, but there's a perfect square in that, right? Okay, so this is gonna be 4 times square root of 4 times square root of 2, all over 8, right? So that gives you 4 times 2 root 2 over 8, which is equal to.
She multiplied by square root of 8 also here.
Does that make sense?
She just multiplied by what was on the.
Yeah, I did them all a little different each time. Sometimes I went ahead and simplified, and sometimes I just did the square root of the whole thing. There's so many ways, I mean, there's.
Right.
There's.
I did 14 like you did. So I had 8 over 8.
Yeah, there, and sometimes cause I know I just simplified this one, but sometimes I just left it under.
It works.
And the first time I did this one on my paper, I